Hello students, so in this lecture we will be discussing about the heat treatment process taking place and we will observe the change in and what the heat treatment process does on the macrostructure as well as the hardness and why we will try to form a structure property correlationship, try to understand it. So the sample that has been taken is a mild steel, or it is also called a low carbon steel, and it's also a low carbon steel, and the carbon percentage in mild steel is between 0.05 to about 0.3% weight percent. Now these mild steels are ductile due to the amount of low carbon present in them. They are ductile as well as malleable. So that is the reason most of the construction areas, the construction designs, the manufacturing designs, as well as the automobile car body parts are formed by mild steel. Now, now this is how the microstructure of a mild steel looks like, and you can see the word "as prepared" is written here. So as prepared means after this steel has undergone polishing, after the sample that has been provided, it has undergone polishing. By polishing, there are a few steps by which a polishing is done. Polishing is mainly done to see the grain structure or the microstructure clearly. Now there are certain steps in the polishing. The first step is polishing with an emery paper. So you can see a YouTube video has been made before how the polishing is done. Now the single stroke, now there are ways, there is a technique by which the polishing is done. It's not that it's a random rubbing. First of all, you need to provide a single stroke, keep on doing a single stroke till one of the faces is polished, and then you need to rotate it 90 degrees so that the other one gets polished as well. So this is how it has been done. After polishing, this is where it is gets further polishing by rotating wheel. So now we have the sample. Now Vickers hardness test is done. Is a process by which we can find out the hardness of the material, and by Vickers hardness, the process involves making an indent of square shape and finding out the diagonals. So D1, this is D2, and the Vickers hardness is 1.8 approximately 5, the pressure applied divided by d square, or the force applied. And this force is mainly in kg. So the pressure applied turns out to be kg force. So if a 5 kg force is being applied, a 5 kg weight is being applied, so the force it creates is 5 kgf. That means you need to multiply it by 9.8 10 to the power minus 9.8 meters per second square. So this is how the Vickers value is obtained. So in the case of the mild steel, we get hardness of about 140 HV has been obtained. Now, after this as prepared sample has gone polishing and we have seen the microstructure, now the process of heat treatment will start. Now the heat treatment will be done in two categories. First one we will see is annealing. Annealing is we put the sample into a furnace and we heat it, and the heat was around 850 degrees centigrade. The reason of taking this to 850 degrees centigrade is becomes clear when we look into the phase diagram, iron carbon phase diagram. So this is the carbon weight percentage, and this is how things work. This is where your austenite formation takes place, and this is close to 850 degrees. So what we are looking for, we would like to cool it from austenite so that there is an eutectoid transformation taking place. That means the austenite is converted into two solids, solid to solid. One is your ferrite, another one is cementite, 3C. Now at around this region, a stable structure of cementite and ferrite is formed, and that is called a pearlite. So in the case of the as prepared sample, that when it has not undergone any sort of heating, you can see that it consists of some white and dark spots. So the white ones are ferrite, having a BC structure, and the dark ones are pearlite. They are having a lamellar structure. That means a combination of alpha and Fe3C arranged in a lamellar fashion, and this lamellar fashion becomes clear if we increase the magnification. So you can see that this is the different pearlitic crystallites formed, and if you increase the magnification further, you can see that this lamellar structure are existent in these regions. Okay. So this is pearlitic transformation. Now why it is called a pearlite? Because it looks like a pearl, and at this stage the next process is we go for annealing. That is simply we are increasing the temperature. That means we already have alpha. We are already here. We are increasing the temperature. We would like to go towards the austenitic phase, and then when it has reached the austenitic phase, we will the reverse process of cooling will start, or it is called actually the hardening process. Now the hardening process can be done in three different ways. Either it's air cooling, that means you allow the sample to cool inside the furnace, air cooling, and it is also called normalizing. Secondly, we use some external stimulant or external effect to cause a higher rate of cooling, and that is when we are using oil. So that is called an oil cooling, or we are using water. It's called water cooling. So all these three cases, this austenite phase again is going downwards. This is a macrostructure of an annealed sample. You can see the pearlitic zones have gone down because of the rate of or the cooling or because of the cooling, sorry, because of not cooling, because of the temperature rise. Okay. Now out of these three coolings, normalizing, water cooling and air cooling, the one which has the highest cooling rate is this one, water cooled. So as as the austenite, it uh, cools and actually it forms martensite. uh, it follows the C curve, it may not form the martensite. So it has to come without following the C curve, and for that we require the rate of cooling should be very high, the highest among the three processes. So we get the martensite without following the CC curve, and martensitic phase is considered to be the hardest phase in the pattern carbon diagram. Next, with a slower cooling rate is now another thing is that the shapes are needle shaped. The martensite formed, or a little bit of combination of martensite and benign, they are needle shaped. That means they are having very high concentrations at the tip. So this is actually sometimes not desired, because these high needle shaped tips at this point, due to their sharpness, there can be chance of stress concentration, which can lead to fracture of the whole system, or the whole material. So that is why a process called ostempering is done. It is basically sort of manipulation where the needle shapes are from where the shapes of the particles formed are tried to make them little more spherical, so that the stress concentration is somehow not as severe as in the case of needle shaped. It's called ostempering. Now the next rate of cooling is where the benite is formed, from austenite to benite, and it actually follows the C curve while cooling, and the particles of the crystallites forms are not lily shaped, but they are leaf-like. And martensite, although is hard phase, but the hardness of martensite is less than the hardness of the hardness of benite is less than martensite. And lastly, there is an air cooling where you allow the sample to get cool inside the furnace itself, and the hardness of air cooled samples are the least among the three cases. So martensite hardness is more than I should say oil cooled, water cooled. Water cooled hardness is more than oil cooled hardness, formation of benite, and air cooled, this is only formation of ferrite and Fe3C. The hardness is the least, and also you can see there is formation of alpha, so that is also an indication that the hardness gets reduced. Now the elemental composition where of these macrostructures is not possible in an optical microscope, and for the element composition we need to do the EDAX or EDX, and it is mainly associated with scanning electron microscope or transmission electron microscope. Another thing is that the microscope that has been used here is called an inverted microscope. Inverted microscope means the sample is kept at the top, whereas the lenses are in the bottom. Okay. Had it been opposite, then it would have been a normal microscope. Now, another interesting aspect that needs to be discussed is the polylytic phase In the as prepared sample, in the annealed sample, there are stress. But in the as prepared sample, you have the mechanical stress, whereas in the case of an annealed sample, we have thermal stress. Now, in the case of as prepared samples, when the biologic structure has formed due to the supply of some external force, so this is how the lamellar structure has taken place. Now, you may ask that why the structure takes place, and the answer to this is that the diffusion of the carbon that takes place that takes place and forms different phases is not uniform, is anisotropic. And there is, in fact, there is a diffusion flux, diffusion tensor existing, where you have 9 different components for x, y, and z directions and the components. So due to this anisotropic nature of diffusion, you get carbon concentrations differently diffusing and differently present in the macrostructure, and actually this gives to rises to the different phases.